remember that it's the ratio of the leading coefficients. And so if your top has a 3 and your bottom has a 1, we're playing this game because they're both degree 3. So when the degrees match, you take the leading number. So we know there's a horizontal asymptote. Like we could even put it in if we felt like it. It doesn't really matter, but eventually you're going to get one right there. Horizontal asymptotes don't like cancel out or go away, right? You get one, it's stuck there. Um, that's not what I wanted to talk to you about. What I wanted to talk to you about is now exposing kind of the real down and dirty nuts and bolts of this function. So in order to do that, we have absolutely got to factor. So we're going to take the top of this function and we're going to pull out 3x squared. And that's going to leave behind what? You pull 3x squared out of the top. What are you left with?
X plus 2.
X plus 2. Good. Kind of a factoring flashback here. I'll wait till y'all have your rulers before I press on here. And then the bottom, again, is just factoring. The factoring is so important because what it does is it allows us to see the things that aren't going to stick around for long. And so on the bottom, what can I do to factor x cubed plus x squared minus 6x? Take x out, first of all, right? That's a huge thing to say. So I'm going to pull x out, and that's going to leave me with x squared. Go ahead.
X minus 6.
Perfect, just like that. But you know, the thing about factoring is like you don't want to just do one thing and then pat yourself on the back. You want to factor things completely. You want to break things down to their very lowest form, I guess. So how does this trinomial factor down? Perfect. So the x squared plus x minus 6 has a pretty short life in this problem. We convert it down or break it down into x plus 3 times x minus 2. So at this point, it is as broken down as it's ever going to be. We've got every possible factor. I mean, the only thing you do to strip it down a little bit more would be to write the top as 3 times x, but that's really just kind of overkill. So at this point, let's talk about the discontinuities. Thank you for being quiet, air conditioning. I'm going to break that thing. What do we see on the bottom down here? How many vertical asymptotes would you say there are going to be? You say two, and I agree. Why not three? Because I see that there's a possibility to make that equal 0. I see that there's a possibility to make this equal 0. And I see that there's a possibility to make this equal 0. You would agree.
Yeah.
And remember that,
Would equal 0.
well, the same thing would happen if you put -3 in, and the same thing would happen if you put 2 in. The denominator is going to equal 0 if you use any of these. What is special about the yellow one? Yes. And so it's a removable discontinuity. And this is one time where maybe writing the 3x squared all the way out, kind of like really fully buck naked, would actually maybe be beneficial if I wrote it out as 3 times x. Then it would be more visual for us to see that, hang on a second, this x and one of these x's can cancel out. And just like we saw yesterday, it's a removable discontinuity, which means it no longer counts as a vertical asymptote guy, but it is a hole. So the fact that this can be canceled with this means there is a hole at
0.
x equals 0. And again, if you want to know the y value of the hole, not if, like you need to know the y value of the hole, you're going to take that 0, that x value, and you're going to plug it back into the function post reduction. The post reduction, I guess you'd call it. It's a function. We'll call it the post reduction. What happens if I put 0 into this purple function over here? Your answer ought to be relatively quick. You think it just comes out to 0? It does. And the thing about it is, like, if you think about if you put 0, that's this guy, I'll underline him for it. If you put 0 in right here is all you need to know. What's 3 times 0?
0.
0. And at this point, it doesn't matter what 0 multiplies by. It's 0 times the set of parentheses. And I don't care what the parentheses come out to equal. 0 times anything is just 0. But it gets even sweeter You could put 0 into those bottom x's, and you should give exactly 0 craps as to what it comes out to, because 0 divided by anything is 0. So we can safely say that there is a hole at 0, 0. So the origin on our graph is actually going to be a hole. But there's more. So it's at this point that we've kind of done everything we could. I'm not sure why I went in the order that I did. It just felt like organically correct to go there. But now we need to go back and talk about the vertical asymptotes. Where are the vertical asymptotes at? I apologize for the noise. It's the air conditioner, and the wind outside is causing there's like obviously a pipe has to be vented to the outside, and it's causing the water in the air conditioner to gurgle. I didn't know if it was distracting you or not, but that's what. What's that?
It was you during somebody back there was just.
No, it's the air conditioner. It's been doing it quite frankly for like the last 5 hours. It's a wonder I haven't lost my cool yet. So
6 or 7 hours.
Oh boy.
Is that what he said?
Well played. Well played. Um, you should agree that there are two vertical asymptotes in this problem. There's going to be a vertical asymptote at one of the places where the bottom equals 0. What's one thing that could still make the bottom equal 0? -3 is a perfect answer. -3 would make this red egg equal 0. And again, if I can make the bottom equal 0 and I can't remove the bad guy by canceling him at the top, it's going to be an asymptote. And then there's one more place that I can make the bottom equal 0. What is it? It's x equals 2. So this is kind of what I wanted to dive into today was, first off, the skeletal structure of your graph. I didn't want you to go home this weekend and just think that every rational function has one vertical asymptote and one horizontal asymptote. It's just not true. We'll see rational functions that have 3 vertical asymptotes. You'll never have more than one horizontal, for the record, but the verticals can be as numerous as the problem calls for. So we're going to draw a vertical asymptote at -3. And we're going to draw another one at +2. And now for the first time ever, we get to see a kind of a higher level buffed up difficulty rational function. The way I view this is that there are 3 regions because this is a function, and I really am almost done, but I need you to keep listening. Because this is a function, the graph quite literally cannot have an arm here and an arm here, right? You know that about functions, that to be a function, you can't ever exist above or below yourself. So the way I view this, my logic is this. There's a region over here called like region 1. There's a region in the middle, like region 2, and there's a region over here called region 3. The graph will exist once in each of those regions. So what we're going to do is, like before, we would go through and we would test out just one point to the right of the asymptote and one point to the left, just to kind of get our feelers. Here, we're going to have to test a few more than that so that we can get our head around where the graph goes. So let's start with region 3. 4 is an excellent answer because if you go to where x equals 4, that's right here where the arrow is pointing, that's safely into region 3. And it's not going to be everything I need, but it's at least going to tell me, like, generally, where is this curvy arm of the graph going to sit, right? We know it's either going to sit up above in this corner or sit down below in this corner, but putting in x of 4 is going to be huge. So if you put 4, and I'm going to erase some stuff since I'm recording, I can do that because if anyone got upset, they could just like hit rewind or something. So I'm going to get rid of all the stuff that I don't want to be there anymore. I can totally do that. And this is my nice cleaned up function now over here on the right. So if I do what Zach said, if I put in the number 4, I just have to grind this out. It's just a math problem. And these do get a little bit more annoying. So what is 3 times 4? 12. And what's 4 plus 2? 6. So the top becomes 72. You think, oh my God, this is crazy. But it's not as crazy as you think. So like the bottom, if you put 4 in place of the x's, 4 plus 3 is 7. 4 minus 2 is 2. 7 times 2 is 14. He's he's gone because he canceled out, remember, with one of the X's on time. So that's why I kind of did some cleanup so that we didn't have any old stuff to worry about. It's all gone. So 72 over 14 is probably about five. It's a little bit over five. And so I can say that five and change, it's probably like 5 point.
57.
And honestly, I don't even think it's very high at all. I think because if you think about it, if you go 5 times 14, you get 70, and you only have 2 out of 14 left. So I would bet it's like 5.1. So that's pretty close.
Yeah, what 5.1?
I'll take it. Good. All right, nailed it. So I'm going to head over to 4 and 5.1, and I'm going to put a dot. And that's going to pretty much tell the truth now, spell the whole story of where I need to be. So 4 and then go up to 5.1. It's probably right about there. And at this point, oh, I forgot. Where was our holds at 0, 0, right?
Yeah.
So at this point, let's just put in a little bit more, and I'll show you a trick. I haven't given you your fancy calculators yet, but I think I will probably on Monday because there's a great way to use your calculators to make a table where you could just program in like the purple function, and then you can have it make you an XY table, and it saves you a ton of time with like all the grindy work. You could appreciate that. Um, Remind me, that'll be a good thing for us on Monday is to get those out, make sure they're all charged up. You got to take forms home to assign because they're like $135 or something. But let's get that done because I think we could start using them now for graphing. Um, Anyhow, let's test like 3. If you put 3 in place of all the X's, on top, you're going to get 9 times 5 is 45. And then on bottom, 3 and 3 is what? 6 and 1 makes 6. So that's about 7.5. So at 3, I'm going to go to 7.5. And now I think it's pretty obvious the way the graph is behaving at this point in time. Okay. We're not going for like masterful 100% Desmos quality precision at this point. I think maybe I would do one more, like 5. What is that? 15 times 7 is 85. And then 5 plus 3 is 8 times 3 is what? 24. So that's roughly about 4. So if I go to 5, predictably, it's right around 4, something like that. So I have enough data at this point to make a pretty good sketch of what this side of the graph looks like. And remember, it's just going to come down and just sort of approach asymptotically like that. So region 3 is boom off our list of stuff to worry about. Region 2, I will tell you that I've seen these graphs. Well, this is kind of a stupid thing to say. These graphs can behave 4 different ways. I'm going to sketch them all as soon as you're ready to look up here. I'll show you what they can do. Option 1 is, and don't try to write this down because I'm going to go kind of fast. Option 1 is the arm in the middle can go like this. Got it? Option 2, the section in the middle can go like, oops, not like that. It can go like this. Option 3, it can go something like this. And of course, you probably know where I'm going with this. Option 4, it can be sort of a modified parabolic sort of situation in the center like this. So this one we're going to need this. This is the one we're having the calculator in the table. You're going to really appreciate that. It's going to help a lot because I need a few points in the center and it can get a little bit annoying. So let's figure out what's going on in the center of the graph between the 2 vertical asymptotes. 0 is a great answer. We know that 0 is going to give us a hole. So let's not do 0. Good call. Whoa. So we know there's a point right here that's a hole. So let's do like 1. Thanks for the reminder on that there, Senator. If we do 1, you just want to be fast with your basic math and, so 3 times 1 is 3, 1 plus 2 is 3, 3 times 3 is 9, and then the bottom is 4 times -1, which is -4. And that's going to come out to -2.25. So I can go to 1 and graph the point -2.25, which is right about here. But if you're paying attention, then you know that I still don't have enough data to really commit to anything because you would agree that I could make the graph go like this. Whoa. But I could also make a case that the graph goes up like this and then comes back down like
Skip
this.
the whole.
So that's why we have to have a little bit more information as to what he looks like. So we could do -1.
It's like, you know how would it be like negative infinity to 0 and then put like year, whatever.
Let's not go there right now. Let's talk about that in a bit. I'm kind of hanging on just barely here by it. So let's just, I hate that thing. So -1. I'm going to change my yellow numbers, just kind of working around here. So if I put in -1, I get -3. -1 plus 2 is 1. Top equals -3. And the -1 down here gives me a 2 and a -3, which is -6. So that answer is 1/2. So at -1, I have a y value of 1/2. And I'm feeling pretty confident at this point, but I want to do one more. The graph still could trick me. The graph still could go like this. It could come up, it could go through this, and it can duck back down like this. They're not, these parabolic sections in the center are not symmetric like an actual parabola. They are not parabolas. They just have that vibe to them. So it can be a little bit of a tricky dog. So let's do one more and just make sure that we're revealing the right picture here. So let's do -2, which is what you wanted to do from the very beginning. I know, sorry about that. But it was coming. I knew it was coming. So if we do -2, we're going to go 3 times -2 is -6. -2 plus 2 is 0. And at this point, you stop because, and I'm really glad we did this because -6 times 0 is 0. 0 divided by anything is 0. So we know the answer is 0. And so the graph is actually going to cross back down through right here, which now tells the story. There's no way around the fact that it's going to behave like this. It's going to come up. It's going to go through here. It's going to hit this. It's going to max out somewhere in here, and it's going to dip back down like this. And that is not one of my finer attempts at an artistically quality graph, but I'm just going to leave it there for you to marvel at. Rest assured, the graph will only do that in the middle, and now region 2 has been covered. And of course, as you would guess, we head over to region 1. 6. And generally what you're going to find with these functions is wherever the one arm is, the other arm's probably going to be with it, like across from it. But that's not to say that it couldn't be down here, because I suppose it could be. But I find often that they're kind of side by side, because you get that one in the middle that's like the alternator, and then the third one kind of brings it back. I don't know if that made any sense. Yeah, any -4 or -5 are both fine. It just doesn't matter. I'll ask Christian. Christian, do you want to do -4 or -5? -5 it is. So if we put in -5, that's going to give us 3 times -5 is -15. -5 plus 2 is -3. So the top equals 45. And then if you put in -5 on the bottom, you get -2 and -7, which makes 14. And we would all agree that's about 3, right? 3 times 14 is 42.
Yeah.
So 3 and change plus times 14 is a little over 42. That's what we're looking for. Bottom line is it's 3 and change. 3 point something small. And that's really enough information for me to just know what I need to know at this point. So I can go to -5, and I know that I'm at 3 and change, which means I am above the asymptote. I'm up here somewhere.
Asymptotic.
Got it? Which is very interesting that it's that. Oh, snapdragons. Thank you. I was going to say, why is that so darn close down there? There you go. So then we can assume then that the symmetry is going to continue to exist. Yeah, let's do another one just for shiggles. Let's do -4.
Yeah.
You better now, Zach? -4?
Yeah,
You like that? So 3 times -4 is -12. -4 plus 2 is -2. Top equals 24. -4 on the bottom is -1, -6, which makes 6. Which, oh, how cute is that? We got a perfect 4. So at -4, we're going to have a perfect 4.
Which means it was a little thing like this.
Isn't it interesting that it doesn't preserve the same like symmetry over there? That's weird, right? But I think we have a good enough picture now of what it is going to do. And these arms they're not going to be the squiggly ones. You're not going to see snakes on the arms of these rational functions. So it's going to come down like this. and it'll fly asymptotically like
That's
that.
kind of flying away from the asymptote there. I don't think that's pretty.
I didn't mean to, but anyways, and it took longer than I wanted, but that's kind of what I wanted to dive into today. It's not like a complete lesson, but it's a lot. So now that you've got like higher degrees to work with, you have more factors that are going to pop out. More factors create more asymptotes, and more asymptotes create more regions. Yeah, so that's that. Anyhow, why don't you go ahead and get back to work? No need to finish these. Get back to work on that assignment, whatever it was, number 22, and then we'll pick this up on Monday.
Do you want to know what old MW did last night?
Oh,